All right, so people can still see my screen in full screen mode, right?
Yes.
All right, great. So I'll very quickly go over the motivation for the lab part that we'll try to spend most of the time with this module on. And the focus will be on implementing relatively complicated physics using ab initio tight binding models using as simple as possible of a Python code. So it's going to be a prototype code. It's not going to be necessarily the highest performing code that we would use for production calculations, but it'll illustrate all the concepts, and this is kind of how we initially develop new physics in the computational material science research that we do. So uh, the topic that we're going to work on today is to predict uh, carrier dynamics in plasmonic metals from first principles. So I'll give you a brief introduction to why we care about plasmonic hot carrier dynamics, and present to you some of the results that we've been able to get in the past using calculations of the type that I'm going to show you today. I'll then spend a little bit of time talking about ab initio tight binding models and what the physical expressions are that we are going to build code to evaluate. And we're particularly going to talk about maximally localized Vanier functions and Vanier interpolation, which we will look at for electronic properties, phonon or lattice vibration properties, and finally, if we have time, for the electron phonon interaction. So let's first start with plasmons. Maybe many of you are familiar with this. Let's take this cartoon picture of a metal with all the electrons displaced to one side. When you have this, you have a net electric field due to the dipole introduced here, which gives you a restoring force, and all the electrons can oscillate back and forth relative to the positive charge of the nuclei. And that happens at a particular resonant frequency, which is the plasmon frequency, specifically the bulk plasma frequency. If you now have a nanoscale material or the surface of a metal, a very interesting thing can happen where you have the real charge oscillation of the electrons, which can couple to the virtual charge oscillations of electromagnetic waves. And you get a standard avoided crossing, which happens in wave physics and also in quantum mechanics, where the charge oscillations and the electromagnetic waves hybridize, giving you this lower and upper mode as shown here. So we are particularly interested in this lower mode, which is called a surface plasmon polariton. And the reason for that is at very low frequencies, it just follows the dispersion relation of a photon. This is omega versus k, which has a slope, which is the speed of light. However, as you approach the surface plasmon resonant frequency, which is some factor smaller than the bulk plasma frequency, you see that the wave vectors become much larger for the same frequency, right? So this means that you have the same frequency oscillation at a much shorter wavelength. And this allows you to bring optical physics from the wavelength scale to a significantly smaller length scale, which happens to be the skin depth of the metal, which for good plasmonic metals is on the order of 10 to 20 nanometers at the relevant frequencies. So this has been used for a number of interesting science demonstrations. For example, you can have quantum optics that could be shrunk to the nanoscale. So people have demonstrated that you can have two plasmon quantum interference, similar to how you can do two photon quantum interference at a much larger scale, but now down to the tens of nanometer scale. So the ideal use of this would be that you could take photonic devices, which would typically be microns in size or larger, and shrink that down to the nanometer scale. However, this has never been quite achieved in any kind of practical way for one major limitation. Plasmons can decay very quickly to produce electron hole pairs in the metal. That, however, can also be used rather than just be a loss mechanism. So there have been in recent years, maybe starting around 2010, there has been a significant focus on exploiting the electrons and holes that are produced due to surface plasmon decay. So um, so I'll show you an example here where you can use this for a nanoscopy application where you're looking at the interface structure of a material by injecting hot carriers into it from a tip, which you then scan across the surface. And you can get significantly better resolution with the plasmonic case because you're able to focus the light down to that tip. Um, One area we particularly focused on was in plasmon driven chemistry, where you have light that is plasmonically coupled into a metallic nanostructure, right? So you get a resonant coupling, which strongly produces electrons and holes within the material, which can be collected to drive chemical reactions. But in all of these cases that were there when we started working on this a few years ago, the efficiencies were really low. So what we wanted to do was to understand the fundamental theoretical mechanisms behind plasmon decay to hot carriers so that we could understand the efficiency limits in these materials. So, very quickly, the simplest way you can think about optical absorption in metals is to look at the dispersion relationship of electrons. So, this is energy versus momentum of a free electron gas. So, that's just a parabola. If you compare the typical momentum of photons at energies that correspond to the electronic scale, they have very negligible momentum. So the simplest way to think about it is photons of a few electron volts have wavelengths on the order of hundreds of nanometers, but electrons have wavelengths on the atomic scale, which is about 100 to 1,000 times smaller. So the wave vectors are much larger for the electrons, and the photon has a negligible momentum in comparison. So you need to do a vertical transition in order to conserve momentum when you take the energy from light and excite a low energy electron to a high energy one. So in a bulk material, this doesn't happen with any real probability. But in a nanoscale material, you can think that the confinement due to the nanoscale essentially makes momentum no longer a good quantum number so that it is not precisely conserved. And so there is some finite probability that you can do this transition. And this is it's that's sort of a hand waving argument. You can make that a little bit more formal by looking at the matrix elements between initial and final states for photons in a bulk material compared to one that has a surface. So either way you look at it, when you have a finite geometry, the surface breaks the translational invariance and can provide momentum, allowing these kind of excitations to happen. So you expect that the smaller you make the particle, the more absorption you get within that. And this is precisely the type of analysis that had been done before ab initio methods could be used here. And people had looked at spherical particles of various sizes, looked at what, tried to predict using that free electron model, what would be the number of electrons and holes compared to the Fermi energy, excited as depending on the size of the particle and a model for how long the carrier lives after it is excited. Right. So, up until this point, any questions? Right. Yeah, please stop me at any time if you have any questions. So what we wanted to do was we wanted to understand how would the band structure of real materials affect this, and whether there are additional mechanisms and how they would all contribute to it. So in a diagrammatic sense, the way we could think about this, so a question on the chat. If possible, it would be great if people unmute their microphone and ask the question, because it's a little, I have only one screen, so it's a little difficult to go back to the chat window. Um, do the surface politons form single photons or a beam of them? Um, that really depends on the excitation intensity and how it's done. For the single photon or single plasmon interference experiment that I had mentioned, they really go down to the limit where they're trying to have a single plasmon mode quantum mechanically excited at a time. But if you are exciting with a much higher laser intensity, you typically will have an ensemble of these plasmon modes all excited together, right? So depending on the geometry, depending on the incident light intensity, you could do any of those. Does that answer your question? Okay, great. So, um, here I'm showing you the band structure of a typical plasmonic metal, specifically gold, and it is still energy versus momentum. The only difference is that the momentum is now on the Brillouin zone of this material because this is a 3D periodic crystal that we're talking about. So, what is shown here is wave vector following a particular high symmetry path along the Brillouin zone. Now, the previous mechanism that we had discussed can still happen. You can kind of see these parabolic band structure regions in addition to a lot of other bands present in this real material. So the previous mechanism is still possible where the surfaces can break the translational invariance so that momentum is no longer a good quantum number and give you a finite excitation probability. But in addition, you now have the possibility of doing direct excitations from one level to the other, right? So that corresponds to a photon coming in, taking an electron from a lower energy and going up to a higher energy. By the way, do people see my cursor? Just want to check that before going forward.
Yeah, we can see it.
Okay, great, thanks. So in addition, when you have a crystal, you have alternative ways you can get momentum. And one of the most important ones is from lattice vibrations or phonons. So phonons have very low energy compared to the electrons, but they have momentum on the same scale as the electrons. So effectively, you can think about the phonon as providing momentum but not energy, and a photon as providing energy but not momentum. So if you absorb both a phonon and a photon at the same time, you can do these uh, non-vertical transitions or these diagonal transitions where you get momentum from one and energy from the other. Right? So that would be summarized by a Feynman diagram as shown here, where an electron gets momentum from a phonon. You have a virtual electron state, picks up energy from a photon, and goes to the higher electron state. So it leaves behind a hole in the initial state and an electron in the final state. So in a real material at a particular dimension, all of these mechanisms will contribute to different degrees depending on the size of the particle and the energy of the photon or plasmon. Of course, this is also going to depend on which material you're talking about. So what we did is we developed a ab initio tight binding model framework that allows you to couple electromagnetic simulations to get the plasmon modes and frequencies, electronic density functional theory calculations to get the electronic states, and also the phonon states, and all the interaction matrix elements between them. So diagrammatically, that can be summarized in terms of propagators for each of the three types of excitations or particles we care about, and the vertices connecting them. And using these, we want to be able to evaluate arbitrary diagrams. For example, this phonon assisted plasmon decay, which I mentioned on the previous slide. So each diagram like this corresponds to a particular expression in terms of the matrix elements and energies. And we will try to evaluate, we'll stick to simpler ones than this process. But the goal of what we do in the next part is to evaluate processes like this by computing Fermi's golden rule on the matrix elements of the of electrons interacting with phonons and light. So using that, we were able to show what the contributions of various mechanisms as a function of energy are for different particle sizes and so on. I'm going to skip ahead a little bit in the interest of time here. Um, we can look at the energy distribution of carriers produced in various materials. So what these plots are showing, and we are going to make a plot like this later. This is showing you what is the probability of exciting a carrier. So holes on this side, electrons on that side, relative to the Fermi energy in the center as a function of plasmon or photon frequency, which is this axis going in, right? So this is electron energy and this is photon energy. So infrared photons are here and ultraviolet photons are at the back with the visible range coming in the middle. So you see a transition from indirect excitations, which are the only possibility at low photon energy. So these correspond to the non-vertical transitions. And once you are able to do the vertical transition, that's where it switches to blue. You end up with this much more electronic structure dependent carrier distribution. So you see these hills, which are at high hole energies on one side and low electron energies on the other side, compared to these plateaus that equally distribute the energy between the electrons and the holes. So depending on the photon energy and depending on the material, they all have different interband thresholds. You can control the distribution of energy between the electrons and holes quite precisely, right? But that's only the first step in utilizing plasmons and holes, plasmonic electrons and holes. This very busy picture shows you what are all the other possibilities that can happen. So we are right now at this stage where plasmons can decay to electrons and holes by a variety of mechanisms. But then these electrons and holes need to transport through the material to reach the surface. And in that process, they can end up losing their energy by electron scattering and electron phonon scattering, in addition to any surface scattering processes. So this is extremely important to consider in order to determine the overall efficiency. And we can solve the overall transport using a Boltzmann equation, where these collision probabilities between electrons and phonons are evaluated from first principles. So using that, we were able to predict the lifetime as a function of energy for all of these common plasmonic metals. And it's important to note that at the uh, Fermi energy, which corresponds to very low energy carriers, you have a high lifetime and mean free path. But as you go away from the Fermi level, it very rapidly drops. Note the logarithmic scale, where you start from tens of nanometers at the Fermi level and you very quickly reduce down to below a nanometer, right? So in transporting less than a nanometer through the material, you start losing energy. And the center is limited by electron phonon scattering. And as you go further away, you are limited by electron scattering. Okay, I'll skip that. Um, so let's talk about what we need to do in order to get to that stage. Sorry, before that, any questions up to this point? Right. Ask me anytime you have one. Okay. So So what are we actually going to do in practice? So we are going to use electronic density functional theory to get the input information. And all of that is already packaged for you in these files that I've uploaded to the Dropbox. So briefly, what DFT does is it solves the one electron Schrodinger equation in an effective potential. So it gives you the electron eigenvalues, which approximately correspond to the quasi-particle energies in the system and their corresponding wave functions. So from that, we can, in addition to the energies, because we have the wave functions, we can compute matrix elements between various electronic states for an external perturbation. For example, that due to a lattice vibration corresponding to a phonon, or due to the electric and magnetic fields of a photon. Now, the challenge, however, is in order to compute the processes that we showed, we need very large number of K points, where these K points correspond to the block wave vector, because we are solving for these in a periodic 3D material. So getting good convergence in electronic and phononic properties for the types of things we care about require on the order of 1 million to 1 billion K points in the Brillouin zone to adequately converge the energy, which means solving the Schrodinger equation that many times, which becomes extremely expensive. So the way we get around that is to use maximally localized Vanier functions, which are essentially a unitary transformation of these Kohn-Sham orbitals, which are periodic in space and extended all over, into a function that is localized exponentially to a particular location. So this shows you the unitary transformation. So you have several bands indexed by B and block wave vector K. So these are the wave functions corresponding to that as a function of R within the unit cell. We have a unitary transformation at each K that couples the various bands together. And you have this Fourier transform from block wave vector space to lattice vectors. And when you do this process, this Vanier function will always be localized to a location centered on this lattice vector. but you can optimize those Vanier functions to be as localized as possible by adjusting these unitary rotations. So that's the process of generating maximally localized Vanier functions. And this is an easily invertible transition because it's unitary in both spaces. That the band space and the Fourier transform is also essentially a unitary operation. So just reversing the Fourier transform sign and taking the Hermitian conjugate of the unitary operator will give you the inverse transform. So you can go from Vanier functions back to the original block wave functions. Now, why is this important? The idea is we can take any operator, any electronic operator we care about, and uh, evaluate that in the electronic DFT. So we wanted to do that for the phonons and the uh, interaction with light. So for example, for some operator O, you will be computing the matrix elements at a particular k by computing this integral, right? You're taking this expectation value between all pairs of bands at a particular wave vector. If I transform to the Vanier basis, right? If I take the wave functions and convert them to the Vanier basis using what I had on the previous slide, that will also convert the matrix elements of this operator to the Vanier basis instead of um, the block wave function basis. So you'll have two sets of unitary rotations here, a Fourier transform there, giving you this operator in the Vanier basis. However, because the Vanier functions were localized in space with some particular range, these matrix elements in the Vanier basis are now going to be short range, which means that if you make R deviate from R prime more than a certain amount, they will rapidly become zero. So you've taken something that was there at all k's, and you are now getting something that is only present for a small number of R minus R primes. And now you can do the inverse transformation exactly as we did before. And if you look at the whole process, you start with the operator evaluated at a few values of k. You convert it to this Vanier basis, which is localized in space. And then you can now compute the inverse transformation at any other k. And it will effectively give me the value of the operator matrix elements at a different k that I had not originally computed using the DFT. And these transformations shown here are significantly faster than solving the Schrodinger equation for each k. So these Vanier functions are essentially providing a highly accurate and much faster interpolation scheme for calculating operator matrix elements compared to what you had with DFT. Right? So all of these techniques are implemented in our open source DFT code jdftx. If you find this interesting and want to explore more, you can go to jdftx.org to see. Um, we will use pre-computed Vanier data. So we are not going to talk about doing the DFT calculation and generating the Vanier functions and all that. If you're interested in that part, all the files that we get here are exactly from tutorials that are already there on the website. So specifically, if you go to the aluminum Vanier function tutorial on the website, you will see how they're generated. And of course, if you are not familiar with DFT, you can learn how to do DFT calculations on that site. So that's the end of the theory intro presentation, which deliberately was quite sparse. Let me know if you have any questions. We'll transition to the Python notebook shortly. In the meantime, if you haven't done that already, please fetch the files from the Dropbox and unpack them and start Anaconda so that you can look at the start Jupyter notebook so that you can look at these Python notebooks. Do all of you have Python notebooks? I believe looking at the previous modules that you've worked with Jupyter and Python already. So let's start with we are going to start with band structure interpolation. We just discussed that you can interpolate matrix elements between k points present in the DFT. So let's look at how some of these files are stored. We'll read them in, and we'll first warm up by just doing interpolation to plot the electronic band structure of a material. In particular, we are going to work with aluminum for the simple reason that it has fewer bands and it will make all of the calculations that we do here a lot faster than if we did it, say, for gold, which is what I showed most of the results for in the presentation. So many of you would be familiar with the Unix command head. Just to make things simple, here's a quick Python implementation of head. And we can, oh, this is not the skeleton one, right? Let me start here. This is the pared down version of the notebook. Feel free to look at the skeleton and fill it in along with me. Or if you feel more comfortable just running the cells in the filled out notebook, you can do that too. So you might want to have both the skeleton and the full notebook where all the results are already present, open in parallel. So if I look at the cell map file with this head function, it's essentially a text file which has 6 columns. The first 3 columns are linear combinations of the lattice vectors of my crystal, pointing to the adjacent cells in my Vanier Hamiltonian. So the Vanier operators are all stored in terms of Vanier functions at one unit cell of the material, coupled to the Vanier functions at another unit cell of the material, spaced a particular distance apart. And the first 3 numbers here are that displacement in terms as a linear combination of the lattice vectors, and the remaining 3 numbers are the Cartesian displacements between them, right? And for every pair of for every displacement like this, we will have a matrix that couples each Vanier function on one unit cell to the Vanier functions on the other unit cell. Let's warm up slowly. Let's start first by reading in the cell map. So Python makes that really convenient. So let's just use np.load text to just read in this entire file, right? And this is going to give me something that has 6 columns. And I can read in, I can get the first 3 columns that way. And I specifically want them as integers. And the Cartesian versions of this, the default is anyway double precision, so I don't have to specify the type. And I look at the last 3 columns of it, that will give me the Cartesian one, right? So this reads in the cells. There are about 2,450 of them. I've separated out the integer ones. Note that it's doesn't have a decimal point here. And then I have the Cartesian versions down here, right? Now, one thing to note, this data was generated from a DFT calculation that had a 12 by 12 by 12 k-point mesh, which means that it has 12 cubed, which is 1728 distinct k-points. When you do the Fourier transform back and forth, it's a fast Fourier transform, you should get back exactly the same number. However, the number of cells in your Vanier representation is greater than that. So it's more than 1728 by a certain amount. And the reason for this is um, we when we are doing this interpolation, we have to worry about how we treat the cells that are furthest away. So this is like the Nyquist frequency when you're doing Fourier transforms. So the cells that are furthest away, so in this case, around 6 unit cells away, you have an ambiguity. You could either treat them as 6 away in the positive kx direction or 6 away in the negative kx direction. And in order to get good interpolation, what you need to do is you need to preserve the symmetry that's present in the crystal. So what's done here is all of those points that are on the boundary of the k-point mesh, especially those ones that are equidistant from the origin in 2 ways, both versions of that are present, and the data is split between them so that you can maintain those symmetries. So this is going to introduce some additional complication, as we'll see before. But apart from that, essentially all we are doing is Fourier transforming back and forth between the k-point mesh, which is the sampling of the Brillouin zone, specifically 12 cubed shown here, and this discrete set of cells, which are a little bit more than that in number because of this boundary symmetrization issue. Any questions so far, and has everyone been able to get the notebook running up to this point? All right. Okay. So um, now the first question I'll pose for you. We need to know what the basis of lattice vectors are, right? So these are uh, vectors corresponding to each. These are the Cartesian coordinates corresponding to each pair of displacements to the adjacent unit cells, which is a 3 by 3 matrix. We'll need this later. We could read that from the DFT output file, but can we figure that out just from the information above? And how would we do that? Right. So what we have, the information we have so far are the linear combinations of lattice vectors present in the Vanier matrix elements and their corresponding Cartesian coordinates. So can we use these two pieces of information to figure out what the 3 by 3 matrix of lattice vectors actually are? So Adam says take the difference of Vanier function locations in neighboring unit cells. That's actually precisely what's present here, right? So with one reference unit cell, these are the Cartesian displacements to all neighboring unit cells. And these are the linear combinations of lattice vectors to all neighboring unit cells, right? So in fact, three, if we had three such displacements which were linearly independent from the first list and the second list, we have all the information to figure out the three lattice vectors. Right. So we need something analogous to that, except we may or may not have those exact combinations present there. So Adam is suggesting yes, we could look for 100, 010, and 001 in the first list. And if we look up the corresponding Cartesian vectors in the second list, those are going to be our three basis vectors. That's exactly right. But could we do something simpler? I want to do this in one line of code. Suppose that is the constraint. So essentially, this n by 3 matrix multiplied by a 3 by 3 matrix is this n by 3 matrix. So how can I determine the 3 by 3 matrix that from that? It's an overdetermined set of equations, of course. So how do you numerically solve an overdetermined set of equations? So Benjamin says take the first few lines and solve that. You could try that, except it might very well happen. So let's try this. So let's try inverting the first three lines, right? So we could do something like this would take the first three rows, and then I want to multiply a matrix, multiply that with the corresponding Cartesian one, um, first three rows. And actually, it happened to work in this case because it turns out that these first three matrix elements were not linearly dependent. But one challenge could be that depending on which ones you pick, you end up with linearly dependent ones. So this did give you the correct answer in this particular case. These happen to be the lattice vectors for a face-centered cubic lattice. Right? So the 0, a by 2, a by 2, a by 2, 0, a by 2, and so on. But suppose I wanted to use all the information to make sure I don't run into the linear dependency. So Nicholas is saying that we use an SVD precisely. So you use in particular you use an SVD implemented to give you a least squares fit. So you can solve this equation in the least squares sense such that you're using all of the equations to determine this. And that's quite closely related. We are effectively going to do, by the way, you could have also written this way. This invert and multiply can be written in this form, linearg.solve. That's the same thing. But if we wanted to use all of the information, we do this with least squares instead. And we won't restrict ourselves to the first three rows. You can ignore that warning. Right? So this is giving you the same, it happens to be the same result. It also has the singular vectors. We don't need all of that. So we'll discard that and we just get the basis of vectors. Right? So in this case, I'm using all of the information to determine that, not just the first three rows. So it's not going to be sensitive to the specific three that I picked being linearly dependent. Any questions about that? All right. Now let's calculate the reciprocal lattice vectors. This is what we will need in order to compute properties related to the K space that we care about. And the reciprocal lattice vectors just happen to be an inverse. Ben saying confused about what this matrix is telling us. Thanks. So what this matrix is telling you is each column of this matrix is the Cartesian coordinates of one of the lattice vectors of the crystal. So this is telling you that if I go along this first column, I will go from one atom to the other and then so on for each of them. In real space, yes. So these lattice vectors are in real space. So this happens to be in Bohr units, so in multiples of the hydrogen atom radius. So essentially, it's a face-centered cubic lattice. So this 3.826 multiplied by 2 will be the cubic lattice constant of the crystal, and this is the displacement from the origin to the first face center and the second face center and so on for an FCC lattice. Does that make sense? Okay, great. So now so this was in real space. Now we want to go to the reciprocal space, and in this matrix form, the reciprocal space calculation is just inversion of this matrix up to a factor of 2 pi. So I just invert that matrix and I also take a transpose of it. So these are now the columns that are each column of G basis is perpendicular to the other two columns of R basis. That's the definition of the reciprocal lattice space. And for a 3 by 3 matrix, you can show that that corresponds exactly to inverting the matrix. So these reciprocal lattice vectors have the property that when I take a dot product of the reciprocal lattice vector with any lattice vector, so any linear combination of these columns, it will be a multiple of 2 pi. So that waves whose wave vector are a linear combination of this basis will exactly be in phase or commensurate between unit cells on that lattice. That's the definition between the reciprocal lattice and the real lattice. Right? And we will need this below when we are computing properties related to K-space. Any other questions here? All right. So let's gradually amp up the complexity now. We next need to read in the Vanier Hamiltonian. But remember, I said that there was this extra bit that we needed to do because the number of cells that are present in the Vanier matrix elements are more than the number of unique ones. So the Vanier Hamiltonian is actually stored only on the unique cells, which are going to be 1728 in this case. But when we do our calculations, when we do our interpolation, we need to expand that out onto all the cells that are present on the cell map. In order to do that, we also need to read this additional cell weights file. So the cell weights file is stored once and for all on all of the cells. But when we are doing each matrix element calculation, we will need to have it available um, on this full size. But for efficiency, the code compresses all of them down only to the unique cells. Right? So I'll explain more as we go along. So first, we need to read the Vanier weights, which happen to have the dimension n cells by n bands by n bands. Right? So I'm going to read. So this is a binary file this time. So I'll use np.from file. We are reading in mlwf weights, cell weights, sorry. And the default type is double precision floating point, which is correct. So this just reads it in as a list of numbers, right? So let's do this in pieces. The rest of this will give an error, but that's fine. So if I look at the list of this, um, oh, right? So this is just a list of numbers of length 61225. From this, I need to first determine what my number of bands are. So I'll do that by taking this total number of numbers, first entry there, and divide that by the number of cells that I already had access to, converting that to an integer. Right? And I can similarly, oh, that should automatically be an integer. And with Python 3, you have to specifically make that an integer division. Otherwise, it will cast it to a floating point. And then I can take the square root of that. Right? So you happen to have 5 bands. So that 61225 was 5 by 5 by the number of cells, which was 2449. Right? But now I need to convert W1A into that form. So I'll use reshape. Right? So that original single list of numbers is in this form, is now 2449 by 5 by 5. There's just one extra thing that I need to do because of there are all these order conventions of how C and Fortran and all of them store data. So it happens to be that I need to flip the order of the last two axes. So I'll do that using this. Now this is of course specific to the code that the data output by the code that we're using. Right? So that of course doesn't change the overall shape. Then the next part of this, I won't go into the details of this. It's basically just reading, it's parsing the output file of the DFT code, and it is determining what the dimensions of the K-point mesh are, which happens to be this 12 by 12 by 12, right? As I mentioned at the beginning. So it's extracting that from this output file. And then the two lines of code here are essentially computing the index of any K point in this uniform mesh. So the stride and this I reduced index is computing a unique integer index associated with the unique K point for an arbitrary cell. And we will use this to map the matrix elements from the unique set of cells to all cells. Right? So this I reduced is the index, is the unique cell index corresponding to each cell present in cell map. So we will first read in the Vanier Hamiltonian, which which we'll do in exactly the same way as this here. So that's the file mlwfh. So this contains the electronic Hamiltonian, and we can reshape that to the n cells unique, which I've called k-fold prod, the product of the k-point folding times n bands times n bands. But that's not what we want for further processing. For further processing, we want to change this dimension to the explicit set of cells with repetition. So to do that, I will expand this out, and doing that just amounts to indexing this at I reduced. Right? So we'll see the dimensions here. So what I read in, I reshaped into something that had 1728, 12 cubed by 5 by 5. And then by applying this I reduced, I expanded it out to the full set of cells that I had mentioned before. Now, this is almost there, but not quite. We have not yet accounted for the fact that we are now repeating some matrix elements. So we need some weights to make sure that our symmetrization works correctly and we have not overcounted these matrix elements. To do that, we need to multiply by the Vanier weights, which is what we had read in the beginning. Again, this is not going to change the dimensions, but that is important in order to get the correct result. So this is probably a bit strange to look at the first time. So take a second to look at it. Let me know if you have any questions. Most of what we're doing here is kind of the input pre-processing that we need to do before we do the physics part of the code that we'll do next. Eric is asking what is I reduced here. So I reduced is basically I reduced is mapping it's mapping things from the let me just put it in terms of dimension. So I have the not 7. So I have every cell that has a length of 2449. Each of them has a unique index when you map it out onto the 1728. So I said, for example, that +6 and -6 corresponds to the same thing when I have a periodic dimension of length 12. And so there are lots of repetitions like that. Those are getting worked out by using this modulo and then taking a dot product with this stride. I won't go into the details here, but effectively this is computing that mapping of every cell within the cell map to every unique cell within a mesh of dimension 12 by 12 by 12. Right? That's essentially the logic implemented here. And then when I index it this way, effectively what it's doing is it's picking out the cell at the unique location from H reduced and storing that in H1A expanded out to the full cell map with the weights multiplied here. Does that make sense? Great. Okay. I'll keep going. Let me know if you have any questions. Now, what we're going to do now is next we're going to plot the band structure. For that, we need a specific list of k points that go along a high symmetry path. So let me look at this high symmetry k point path. Right. So I have this file called highsym.kpoints in the path, which essentially contains the coordinates of various k points in the Brillouin zone. These are in reciprocal lattice coordinates. Corresponding labels for those k points. So remember, we had the gamma, x, etc. So those are the labels there. And the last index is basically telling me how many k points to create between them in order to get a particular sampling of the k point path. So we're going to read this in. Just to practice once again, we'll do this from np.load.txt. So we'll read this file and uh, I'll use the first 3 columns. Right, I'll get the k points of the symmetric path. If I do the same thing with the third column, I will get the k labels, but I should now specify the data type. It happens to be a string. And similarly for the index, I want to read in something as an integer, right? So I was able to read in the list of k points. There were, of course, more lines than what was shown here. These are the labels of the points in the k point path and their corresponding indices. Okay, just a simple file parsing exercise. Then this next code here, which is not particularly relevant to us, so I won't go into much detail, is essentially going to take these pieces of information and it's going to create a list of k points connecting um, all these high symmetry k points in that path, giving you an overall list which will have 179 k points. Right? So it overall creates a data structure for me with dimensions 179 by 3, where it starts out at 000, goes up to 0.25.25. That was the first one. Actually, no, 0.5.5, which will occur at k point 36. Then from that point, it will go to the next one, which is 0.25, 0.75, 0.5, and so on. Right? So it basically just did the logic of adding in the intermediate k points with the numbers given by this to create a k point path. Right? That's mostly the boilerplate code. But now let's get to the actual Vanier interpolation here. So what we want to do now is we want to interpolate the Hamiltonian to each of the k points uh, on this path, and then we'll diagonalize them and we'll get the electronic energies from that. All right. So first, we need to we remember the steps required. We need to do a Fourier transform. So let me show that here. Right. So O in this case, what we are looking at is the Hamiltonian. So we have, in order to do the diagonalization, we need to do this Fourier transform. This R minus R prime is what is stored in the cell map. This is written in Cartesian coordinates. We'll use the lattice version of it to make it a little bit simple. And we essentially need to do this Fourier transform. So we are first going to compute this Fourier transform phase that takes you from, but we are doing the inverse transformation, sorry. So we are going from the Vanier matrix elements to the block matrix elements. So let me first compute that Fourier transform phase. So I'll have a 2 pi I. The 2 pi comes from the working in lattice coordinates. And I need to do a dot product between, so I need to do the k dot r. So this is the 2 pi I. And I need to do a k dot r where k is each k point in this list. So in this case, I'm calling that k path. Right? And I want to take a dot product against that and cell map. So the cell map contains the r minus r prime. Right? So both of these are, so this is in reciprocal lattice coordinates and this is in lattice coordinates. So I don't need to convert them to Cartesian coordinates. The only thing that changes is I have an extra factor of 2 pi compared to the expression written here. Right? But, oh, sorry, I'm doing this for a specific k here first. So that would just be that. Now, let's just think about this carefully for a second. Cell map has dimensions n by 3 and k has dimensions 3. It's just one k vector. So this should actually be the other way in order for this dot to work. Right? So this will now just be one complex number for each entry in cell map. So it's the Fourier phase for each entry in cell map. Using that, I can compute the Hamiltonian for this specific k point by multiplying the phase and adding that together with the Vanier Hamiltonian. Now, the Vanier Hamiltonian has dimensions n cells by n bands by n bands, right? So this is, so my phase is going to have dimension n cells, and then I'm dot producting that with something that has dimensions n cells by n bands by n bands. All right. And once I've done that, I can get the energies and the eigenvectors by diagonalizing this Hamiltonian. Right. So then I'm just accumulating all those energies together to compute the total energy. Okay, I've actually called it UK dot shape. I've called it UK. Okay, so the dot didn't quite agree. So so the dot really only works when I have up to dimension 2. In order to do this with higher dimensional arrays, I should use tensor dot instead, and I should specify how many axes I'm contracting. So this is basically saying contract the last one dimension of the first entry with the first one dimension of the next entry, giving me something that has those dimensions, right? Which is what I'm diagonalizing down here to get the energies, right? So now I've collected together all those energies to get 5 band energies for each k point in the path above. And this UK, of course, was present for each individual k point. And so that's just a 5 by 5 matrix, which is the eigenvectors, right? Think about that for a second. In the meantime, we really didn't have to do it like this at all. We could just have vectorized over all of the k points together, and that's going to matter as we increase the number of k's that we'll do this calculation for further down. So um, so let me just copy this over. I want to do this for all k points together. So remember that cell map had dimensions n cells by 3. K path had dimensions n k points by 3. So if I take a transpose here, then this is going to give me a dot product for every vector in cell map, dot producted against every vector in k path, right? So this is now going to have dimensions uh, n cells by uh, nk in the path, right? Um, however, below I will want the opposite. So I want to do nk by n cells instead. So I'll just reverse this. I'll do k path first and do cell map dot t. Right. So same logic, but it will now the first index will be nk, the number of k points, and the second index will be the number of cells. Now I'm going to compute the h for all of these together. This time I now have nk by n cells in the phase as shown here, and I'm taking a contraction against the same object. So it's going to give me a result which has nk by n bands by n bands. And then the eigen h function already is vectorized in exactly this way. So if I give it an array of matrices in a 3-dimensional or higher dimensional array, it will do the diagonalization along the last 2 dimensions. So I can just do e comma u is eig of h, and that will just compute all the energies for me all at once, right? So the E is exactly the same as before. This time the U contains the unitary rotations or the eigenvectors for every k point altogether in this 3-dimensional array. And then we can plot that, and that would be the band structure of aluminum. So I'm going to pause here for a bit. Let's look at the couple of code blocks above and let me know if you have any questions. Right? Because this is the key Vanier interpolation operation in effect. right? So the DFT K points, the DFT data that we read in was not actually calculated for these K points, but we are now interpolating to an arbitrary K along this high symmetry path to compute the band structure. All right, while you're thinking about that, let's just do some cosmetic tweaks here. Um, what's shown here so far is a band structure where the energies are in the internal atomic units of the code, which is Hartrees. And doing it in atomic units makes a lot of the physical expressions a lot easier. So we typically tend to do all of the calculations in atomic units and convert it back to something like SI units only at the end. Because E and H bar and a lot of other constants are one or something simple. C is the inverse of the fine structure constant and so on. So it makes things a lot easier to work with. So we'll take the same band structure now and let's do a few tweaks. First, I'm going to limit the range of the X to exactly be um, the end here. So that would be K path, right? So that would remove that dead space at the end there, right? And then we want to get rid of these arbitrary integer indices at the bottom and put in the names of the K points. So we had that, we'd already read that in. So we can do that using the xticks where we give in, I need to remember, I forgot the names there. So we had read in K labels and K index. So if I do K index and K labels, that replaces that with the explicit names that we had at the specific points. We're almost there, but not quite. I don't like gamma spelled out like that. I would rather have the Greek symbol there. So we can do that by expanding this list out. So I'm going to do a list comprehension for label and K labels. If I just did this, it does nothing. It just gives me back the same label. But what I can do here instead is I can now add a conditional here saying um, if label happens to be gamma, then I do something else. Otherwise, I just put label in there instead. And now I'll use the LaTeX notation and matplotlib will fill it up for me. Right? So just to show you some other cool things you can do. Right? Now we fixed the x-axis. We haven't quite fixed the y-axis as it would be standard for a band structure because we haven't yet put it up against, typically you plot it against the Fermi level or the highest occupied molecular orbital or CBM, VBM, depending on the type of material, whether it's a metal or a semiconductor. At the moment, we don't yet have information to do that. In the next block, we are going to come, we could read this from the DFT output file, but what we are going to do instead is we are going to compute the density of states. We know how many valence electrons aluminum has per unit cell. And from that, we are going to determine where the Fermi energy should be if I filled in 3 electrons. And we'll replot this band structure with that Fermi level position based on that. So once again, any questions up to this point with the simple interpolation of the Vanier Hamiltonians? Right. Just stop me if you have any questions. All right. So to compute the density of states, we need to compute this expression. We have the list of energies already, except that we have it now on a regular k-point path. We need to compute this over the entire Brillouin zone instead, not just along the high symmetry path. And we essentially integrate over the k or sum over the k with 1 over nk as the weights, and we sum over these delta functions, which essentially amounts to histogramming the eigenvalues that we have on an energy grid. That will give us our density of states, right? So that will tell us how many states we have per unit volume of the system. This is the unit cell volume. um, per unit energy interval of the crystal. So first we need the unit cell volume. Can anyone help me fill this in? I have the lattice vectors. How do I compute the unit cell volume from that? Yep, the vector triple product, exactly, which for a 3 by 3 matrix happens to just be the determinant. Right? So I just do that. So that's exactly the triple product. Right? So that's the unit cell volume in Bohr cubed of the material. Now we need to compute the density of states. Oh, I actually didn't clear this code. Anyway, it's we are basically computing the energies exactly as before. The only difference is we instead have the instead of the K path, we have a bunch of K points covering the Brillouin zone. And for simplicity here, I'm just doing a Monte Carlo sampling. So I'm sampling a whole bunch of K points in 0 to 1 cubed, right? I do the exact same operation as before, right? So I'm computing the phase as we did before, doing the tensor dot, and then doing the diagonalization. I don't want the unitary rotations, so I just neglect them this way by putting the underscore, right? So all of this is what we've done already, just applied to a different set of K points instead of the path, because I need to integrate over the Brillouin zone. Now I can histogram uh, these list of energies that I have to compute the density of states. Right? And to do the histogramming, I'm going to do that over a particular range. So I have an energy grid of width 0.001, 1 millihartry. Um, and I'm going to go, because looking roughly at the band structure, I have information from about minus zero point 0.2. Now, I don't care about the stuff at the top. The Vanier is only representing the bands up to a particular energy. So I'm going to cut it off at 0.6. I really don't care about it after that. Right? So I'll do np.histogram. The data I'm histogramming is just a flat list of the energies. And I'm going to use the specific bins that I've specified here. Right? And this returns a bunch of outputs, so I'm only going to take the first one. Now, this doesn't yet account for uh, the prefactors that we had in the expression above. So I need to, GS is the spin degeneracy. So I'll multiply that by 2. And then I have to divide that by the number of K points and the unit cell volume. Right? And then the last bit of that plots it. Okay, it doesn't like that should work. Right? So this is the density of states in per unit energy interval in Hartrees per unit volume in Bohr cube as a function of energy in Hartrees. Right? Now, this of course is, we would like to do better. We would like to have a much better sampling of this. But you can already see that this took a few seconds. If I try to increase the order of magnitude here, it's going to start taking longer. Note already that we are doing 100, we are doing 10,000 K points, right? So the interpolation is really fast. If we had to do the same DFT, this would have taken at least a few minutes um, on a workstation. So what we'll do instead, and we're going to keep the structure of the code going forward, we are not going to evaluate it all at once. We are going to do it in blocks, and we'll have some partial progress that we can keep track of. So I'm going to do blocks of 1,000 K points, 100 such blocks, and I will report that I have done how many blocks after each K point. Right? So we just need the same code. So we have the copy this all over. Right? I have that's just saying what I want. Oh, I already have that in the previous cell. I don't need it again. Um, I'm going to compute the DOS due to in blocks. So I loop over block, right? And I'll generate the K points each time. Compute the corresponding, I don't know why I deleted that, compute the energies. So I create a new set of Monte Carlo K points for each block, compute the phases, compute the energy, um, do the histogramming, right? And just add it together. But this time I'm going to do this n blocks time. So I will also multiply the number of blocks in the total number of K points sampled. And as I said, I wanted to print progress. So I'm just going to do so this will just keep printing the number of blocks I've done, so that I have some progress. Right. So now I'm doing 10 times as many K points as last time. So I'm doing this sampling over 100,000 K points this time. Right. And you have a much better sampling now. You can kind of see the parabolic density of states expected for a free electron like metal. Of course, some deviations due to electronic structure details in the band structure, which are beyond a free electron metal. And up here, you should no longer trust the density of states because the Vanier representation works up to a particular energy window, as it's called. And in our case, our energy window stops at about 0.5 Hartrees. If you want more details on that, you can see the tutorial on the jdftx website. So Benjamin is asking, have we sacrificed accuracy by using this approach? Accuracy in what? So we uh, yes, the interpolation is of course an approximation. The states are not going to be the energies are not going to be exactly the same from the interpolation compared to what you have, um, and that you control by changing the number of K points in your original DFT calculation. But usually for most materials, by the time you've gone up to about 10 cube K points or maybe 20 cube K points for some more complex materials, the interpolation actually does a really good job at capturing the energies. If you try to do the density of states from a DFT calculation alone, typically you'll end up with a much spikier looking density of states because it's very difficult to sample as many K points. So in this approach, you can end up getting much smoother and much better sample density of states because you can really control and all the other properties that we're talking about below, because you can really you can make sure that you're not missing any important K point. So the only point where we are making an approximation is in the energy and the matrix element being interpolated rather than calculated for that K. And that's a controlled approximation because you can simply increase the number of K points, which means that you're interpolating less. Does that make sense? Great. Right. So now this is easily parallelizable over MPI. As you can see, these blocks are quite embarrassingly parallel. So even with Python MPI, you could add in, and if you want, you can do that as an exercise. You can split up these blocks over MPI and collect them together. It should be fairly straightforward to do. But we are going to focus more on writing more complex physics. So we'll not worry about parallelization. We're just going to use the sequential version as shown here. Now, the next thing that we'll do is we want to figure out the chemical potential. So we want to find out how far I have to go here in order to exactly get 3 electrons per unit cell. Right. So for aluminum, I have, yeah, so Z val is 3. That's the number of electrons per unit cell. If I wanted to compute the um, number of electrons as a function, if I wanted to compute the number of electrons per unit cell as a function of energy cumulatively. I can do that by using the cumulative sum function. So I just do a cumulative sum of the density of states that I've computed. That's per unit volume. Um, Hold on. Did I do something? Oh, there's one other thing I need to do here, which is not correct. I need to divide this by the density. So the DOS, the histogram function is just computing the number of states within a particular interval of width dE, which I defined above. But when I'm thinking about the density of states, I need to divide by dE for this to be correct. So let me rerun this quickly. Right, because I'm thinking about it what it is per unit interval, so I need to divide by the interval size as well. And while we're doing that, we'll work on this. So I take a cumulative sum of the density of states, but what I'm actually doing is an integral, so I'm multiplying that by dE. And if I want it per unit cell instead of per unit volume, I multiply it by the unit cell volume. So this will be the cumulative number of electrons up to a particular energy, and I want to find out at what value of I want to find out at what value of energy that equals to 3. So I can do that by using interpolation, and I want to interpolate to zval, um, and I'll have the was it E mid? Yeah, E mid as the x-axis and n electrons as the y-axis. So it will basically compute for me, sorry, the other way around. I'll have n electrons and then E mid. So it will compute for me the energy corresponding to n electrons equal to z, right? And so it's telling me that it's 287, so it's somewhere over here. So if I basically it's telling me if I integrate this curve up to that point, I will get 3 electrons per unit cell. So that's my chemical potential, and I can repeat the band structure plot now. Um, Shown there. I can repeat the, oh, I need to recompute the energies too because I overwrote them. Right. Sorry, did I mix something up here? Yeah, sorry. This is, that's for the DOS. Sorry, I mixed two things up here. So for the density of states calculation, we can change the energy unit. So let me start with this. So I will reference my energy to the chemical potential now and switch it to electron volts units. And for DOS, I want to convert that to, so this is now going to be epsilon minus mu in electron volts. And then similarly for the DOS, I am now going to have it in electron volt inverse and nanometer inverse. Right, that's the goal. So uh, so to do that, I will divide by the same unit, which is equivalent to multiplying by the reciprocal of that. So it's DOS multiplied by EV multiplied by nanometer cube. Right. So that's now in a more conventional unit relative to uh, the Fermi level at 0. Right. So that's the Fermi level location, instead of whatever absolute energy axis we had before. And we can use the same kind of referencing for the band structure. And I'll stop with this first part right there. Right. So we have the same thing. We'll get the energies as before. And in plotting the band structure, we'll plot E minus mu divided by EV. Right. And everything else is the same. And I'll put a horizontal line at 0 to indicate the Fermi level. Right? So that's now our conventional band structure plot, reference to the chemical potential with all of the energies there. And if we want, we can cut off the um, x-axis for energies we care about. Okay, so we'll stop here for this module. Let me know if you have any questions. We will continue on with the direct transitions, phonons, and electron-phonon interactions in the second part of this at 1:30 p.m. Note that it's a different WebEx link for that. I'll still be on here for a few minutes to answer any questions. Right. Has my screen shown up? Then we could get started.
Yeah, it's just your browser right now, though.
Yeah. It's all on the browser. So once I switch tabs, it should be there. All right. Welcome back, everyone. So let me go back to the Python notebook that we're working with. And I'll just quickly run through the things that we did towards the end of the previous lecture. So the first part was just getting the files read in and so on. The key action happened in this Fourier transform and diagonalization over here. For the Hamiltonian, we could determine the energy eigenvalues and we determined the unitary rotations just as the eigenvectors of the Hamiltonian. In what we are about to do, we are also going to work with other matrix elements. And when we do that, we will need to switch them into the eigenbasis. So that's one new operation that we will do immediately next. In the meantime, just by looking at energies, we were able to do the band structures if we went along a high symmetry k-point path. Then if we went over the entire Brillouin zone and integrated using a Monte Carlo sampling, we ended up with the density of states, right? Which we optimized a little bit to get a curve that looks like this. Then we determined the chemical potential by finding out the number of electrons, and we were able to reference the density of states and the band structure to the Fermi energy of the metal. Right? What we're going to do next is we're going to look at the probability of vertical transitions on this band structure. So essentially, we are going to be looking for pairs of states, one below the Fermi energy, one above the Fermi energy, at the same K point, and compute Fermi's golden rule for direct excitation. From that, we are going to calculate the contribution to the imaginary part of the dielectric function. Um, from direct transitions. For simplicity, we won't do the phonon assisted transitions here. That would require a little bit more complexity involving both the momentum matrix elements and the electron phonon matrix elements, which we won't do here. So for the direct transitions, essentially what Fermi's golden rule gives you here, the relevant matrix element is the velocity or momentum matrix element that connects electrons between two different bands at a particular wave vector. You have the energy conservation between the initial energy of the electron plus h bar omega and the final energy. So you leave behind the hole at this energy and produce an electron at that energy by absorbing a photon of energy h bar omega. And the probability of this, you require the first state to be occupied and the second state to be unoccupied. That's what this difference between the Fermi occupations is enforcing. And all the other prefactors have to do with connection between the rate of decay of a single photon, which is what Fermi's golden rule will give you, to the energy density in the optical field and so on. So there are some standard prefactors there which you can look at. You can look at textbooks for this, which connects the Fermi golden rule for a single photon decay rate to the overall imaginary dielectric function, which is something that can be measured readily experimentally. So in order to do this, the key quantity that we need to be able to process are these momentum matrix elements. So we will first read them as we had for the Hamiltonian. And then after we have read them in, we will need to do this kind of unitary transformation that we had talked about, right? So it has the same Fourier transformation as the Hamiltonian. But in the case of the Hamiltonian, we obtained the unitary matrices and the eigenvectors just by diagonalization. Now we will need to explicitly do these unitary rotations. So let's start by reading in the momentum matrix elements and the Vanier functions. To do this, I'm first going to copy over the code from the from that we had for reading in the Hamiltonian, and we'll modify that to do this. So I'm going to copy this code over. So we're going to do a very similar thing here. We're going to read in the momentum matrix elements first in the reduced set from a file mlwfp. The only difference now is we don't have just one. We actually have three such matrices, one for each Cartesian direction. So it's the momentum along x, the momentum along y, momentum along z. So we have three operators, n bands by n bands representation at each k point, or rather each unique cell of the Vanier function, right? So overall, my conversion for p Vanier will be very similar. I still need to multiply the weights, right? This part of the operation is exactly the same because this I reduced operates on the first axis, which converts this unique cell index into the overall cell index. So it converts a dimension which is k-fold prod long into one that is n cells long. However, we will need one additional dimension here in W Vanier because W Vanier had the dimensions just n cells by n bands by n bands. To account for the extra dimension, we need to add this none index. Otherwise, Python will complain about the dimensions not being matched. So let me show you that first. So if I do this, you'll have an issue because p reduced, I reduced has this shape. It has this extra 3 here, and we need to help NumPy figure out how to multiply these together. So to do that, we'll do this, and then they'll multiply together as expected. So we read in something that we had this extra dimension of 3 compared to the Hamiltonian, and now we've done the same processing. We've expanded it to the full set of cells, and we've multiplied in the weights. All right. What we will do in the main part of this code next is we will do this unitary transformation, but we'll get there in a couple of cells. We are going to compute the dielectric function on a regular frequency grid. So I'm going to set up a frequency grid exactly as I had the electron energy grid before. I'm going to go up to 6 eV in a spacing of 0.01 eV. Right? And I just have those midpoints of the bins set up for histogramming later. Let me also show you what the result is expected to look like experimentally. So we are reading in an experimental dielectric function, and we're going to plot it in the same units. Emaps is dimensionless against h bar omega, right? So this is what the dielectric function will look like. At very low frequencies, you end up with the dielectric function blowing up. For metals, imaginary epsilon goes to infinity as omega goes to 0. This is essentially the conductivity portion of the response. And far away you get this. So we'll see how our theoretical calculation compares to this, right? So what I'm going to do is I'm going to copy over the DOS code, and we will modify it step by step to get the direct transitions. And this is basically what we're going to spend a significant portion of the time in the second half on. And then the remaining pieces of this are going to be very similar. So be patient with this part. Whoops. Okay, so the first step is exactly as we had before. We go over these blocks, we compute the energies. If we just wanted the DOS, we were histogramming just the energies and we were done. But we are no longer doing that. We also need additional quantities, which is namely the momentum matrix element. So we also had an overall DOS that we were collecting before. right? So we were adding this over the blocks. Likewise, we will be adding uh, IMAPs over several blocks, right? And this is going to be on the frequency grid. Okay, so we are not histogramming the energies. We have to figure out what we need in here. So the first step is we no longer need only the energies. We also need the eigenfunctions because we will need to do the Fourier transformation. Sorry, we will need to do the transformation of the momentum matrix elements to the eigenbases. So this is the energy part. Now the new part here is we will be computing the momentum matrix elements. Right? So the first step of this is quite similar. We will do a tensor dot of the, so we if we look at the momentum makes the expression here, the first part of it is doing this Fourier transform. That is exactly as before. So that will take us from the real space basis to the K basis. But the second bit after we have done that is the unitary transformation going from the band, from the Vanier function space to the band space. So let's do the Fourier transform first. Right? And we can just do a temporary print and try this out. I was expecting it to stop with an error, but it actually kept going. um, so now we within each block we have 1,000 K points, and so we have essentially computed. We have transformed the Vanier functions which were on a particular number of cells. We have now done the Fourier transform, and for each of the 1,000 K points that are randomly sampled for this block, we have this 3 Cartesian directions and 5 by 5 in the Vanier basis. Now, what's left is for each of these combinations, we need to take these 5 by 5 Vanier bases and convert them to the band basis using these unitary functions, using these unitary rotations, right? So, and also I'm particularly interested only, no, sorry, I do need the full, I do need the full momentum matrix elements, right? So I'm just going to do that unitary transformation, and I will have something that has the same shape, but is now in the eigen basis of um, the electronic states. So if you think about what I need to do, I have 1,000 by 3. I have an array of 3,000 matrices that I need to do this unitary transformation on. The simplest way I could think about doing this is I loop over all 3,000 matrices and I do an np dot dot with the u of the appropriate one multiplied by the. So I do a u and a u dagger and I do the unitary transformation. However, that is going to be quite inefficient, especially when the matrices are so small. Right? So it is quite important to vectorize them. And the easiest way to vectorize them here is using the function einsum. So if you haven't used this before, I'll spend a little bit of time explaining how this works. This is absolutely my favorite NumPy function. So we want to apply this unitary transformation. So so we're going to use this function that essentially implements the Einstein summation convention and converts that into a vectorized operation. So the way you do it is you write an x. So first let's collect the operands together. Okay, I see. That's good to know. So you used einsum in another tutorial. All right. So I'll just skip ahead then with this part. So the operands that I need here are going to be the unitary rotation, P, and the unitary rotation. And if I look at the order of operands here, the U dagger is on this side. Oh, I see. Thanks, sure. Oh, so you would have had much crazier contractions than what we are going to do here. So the U dagger is on the first one. So I'll just do the complex conjugate here because I can account for the transpose in the Einstein. And so the indices here are, all of them have a K index. And for the unitary rotations, I just have two band indices. For the momentum matrix element, I have a K index and additional Cartesian direction index and two band indices. For the other unitary rotation, once again, I will have KCD. And when I contract this together, remember I'm not summing over K, so I still have the K index together and I will have AD. The only thing that's left over, you can see that I'm contracting AB, BC, CD, but I also need to transpose on the first one. So I just swap the indices there. So that makes it U transpose. Right? So this gives me the momentum matrix elements in the eigenbasis now because I've used the eigenvectors. Next, we need the and then we can compute the. That's straightforward, right? So that's going to be the matrix element squared that is required here in the expression. And because I'm assuming an isotropic material, I will just need the overall length squared. So I will also now sum over. I will sum over the Cartesian direction. Oh, sorry, there's one more I over here for the Cartesian direction. I will sum over that axis. So this will now have dimensions nk by n bands by n bands. So this should be proportional to the, for each k point, this should be proportional to the probability that I can excite from an initial state to a final state. Right? But of course, that's only the matrix element term. If we look at the overall Fermi golden rule, we also need the occupation factors and we need the energy conservation. Now, the energy conservation, the way we are going to deal with it is each pair of energies contributes to a particular photon frequency. So when we encounter a particular pair of energies, we will just histogram by that energy difference and collect to that frequency. Okay, so let's first look at energy difference. We can do that just as indexing this. So the K index is always going to be the same. And I will index this first along this dimension and then along the second dimension. So this will now compute the energy difference between all pair of states for each K. Let me do this together. I can compute the Fermi occupations from the energies. Right? So that will just compute the Fermi occupations for each energy. And I have a Fermi function difference as well over here. So I'll do that in the same way. Right? And now we are ready to compute this histogram. We can multiply all of these terms together to compute the weight that is present that multiplies each term with a pair of energies. So the only part is just the matrix element squared and this difference between the Fermi occupations. And that gets collected into a particular term with energy difference given by the EDIF. So, so in np.histogram, I'm going to use the same thing. Um, I'm just going to set the weight here. So I'm going to use EDIF as the thing that I'm histogramming by, because that's the photon frequency. And the weight corresponds to FDIF multiplied by P squared. Let me take this term out separately. Right? And I'll put in all the prefactors up front. So in this we have 4 pi squared, E squared is 1, G is 2, so I have 8 pi squared over 3 omega squared, number of k points and omega. So 4 pi squared over 3 omega squared and k omega. With the spin degeneracy factor, that's 8. The effective number of k points that we have sampled as before is nk multiplied by n blocks. I have a d omega for the delta function, exactly like similar to how we had dE for the DOS, and I'll have the unit cell volume. I think I got everything. Let's try that out and see what that worked as. So since I flattened that, I should flatten this as well. And this should be, since I'm collecting by frequency, this should be omega bins. No, I also forgot the omega squared frequency in the frequency factor in the middle. So I should have omega mid squared. Yeah. So clearly this is going to look quite strange. Oh, data has no positive values. I think I mixed up my, oh yeah, the energy difference and the fillings difference have the opposite sign. So that's why it had no positive values. Meantime, let me quickly check compared to the completed notebook that I got the directions of the unitary rotations and so on correct. That always takes some trial and error to get right. Yeah, the conjugate. Yeah, that looks correct. Yeah. I'm actually kind of surprised that worked out the first time, but there we are. No, we are off by some factor. Oh, I forgot the factor of 3, which is for the isotropic average. So I forgot this factor of 3 right there. So as we're waiting for this, any questions on what we did here? So you can see how easy it is to write out a Fermi golden rule rate calculation using this. So once we fix that, we get pretty decent agreement with the dielectric function in this energy range. But there are two things that are not quite right. We get this very sharp peak at about 1.6 eV compared to this rounded off hump in the experimental curve. And we are underestimating the dielectric constant in this region. So Can you think of why? That would be? So this part agrees well. Why are we missing some? We are missing some contribution here, and we get this much sharper peak there. Any hypothesis as to why those might be? So I'll give you the first one. This sharpness of the peak here comes about because we are missing broadenings. We are assuming that the delta function is sharp. Each carrier has its own lifetime, and some of these carrier energies that are far away have quite a short lifetime. So they have a large line width, and the delta function should be replaced by a Lorentzian which has that width, and then you will be able to rectify that shape over there. You can get quite good agreement with the experiment once you do that. What about this region? Why do we underestimate the dielectric constant? So Joel mentioned finite size effects, but we are actually comparing to the dielectric constant of an infinite metal for the bulk material. But yes, if we had a nanoscale particle, that would give you additional contributions. But the experiment here is from the experimental dielectric function is from ellipsometry. So it's a semi-infinite slab of metal. So the remaining piece over here on the left-hand side, note that we are only calculating the direct contribution to the dielectric function. When you are at much lower frequencies, for most of these materials, the dominant contribution is indirect because the phase space for doing phonon-assisted transitions is significantly higher. So because we haven't calculated the phonon-assisted phonon-assisted transition contribution to the dielectric function, we are missing that initial part. Right? So all of that will come from indirect transitions. Any questions so far?
So do you mean like the difference between a direct gap and an indirect gap? That kind of direct versus indirect?
Yes, exactly. So there is an interband threshold. So aluminum, you can have interband transitions at any frequency, but interband transitions really become strong after this threshold at 1.6 eV, which I can show you on the band structure. So you have a band crossing right at the Fermi level, so you can actually find vertical arrows that connect below and above at any energy. But when you are able to reach this split over here, that split compared to the center is about 1.6 eV. So there is an effective interband threshold at that transition, which is what gives rise to this hump here. So you get much stronger interband transitions beyond that, but intra-band transitions due to phonons are always active. They are swamped out by the strong interband transitions above, but below 1.6 eV, that is the dominant contribution, and we're currently not calculating that. Does that make sense?
Yes. Yes.
Yeah, great. Any other questions? So what we've done so far is great. We've been able to match the dielectric function in this energy range, and with similar but slightly more complex code, we should be able to figure out the phonon assisted as well, which we are not going to do here. Now, however, that in itself is not useful. What we can really get from the first principles calculations, which is very difficult to get in experiment, is the energy distribution of the carriers after the light, photon, or plasmon has been absorbed to produce carriers in the material, right? Because you can only sense that indirectly in experiment, either by collecting the carrier in a semiconductor or by driving a chemical reaction. But from the theory, we can directly calculate what the electron and hole energies are corresponding to each transition that contributes here. And from that, we can figure out what the carrier distribution looks like. So that's what we're going to do now. We are going to compute the imaginary part of the dielectric function. But in addition to that, we are also going to calculate the imaginary epsilon resolved by the electron energy and the imaginary epsilon resolved by the hole energy. Right. So first, let's just copy over this code, which is going to be exactly the same. For simplicity, I'm going to define a weight right? So I have my W here and I'll have my edif here. So that we haven't changed anything yet. In addition to that, we also now need to know what the um, initial state energy and the final state energy are in order to compute those IMEPS E and IMEPS H, right? So my IMEPS H for my whole energies are the lower energy that we care about. So um, so this is going to be my energy of the whole is going to be uh, this minus mu, but I want to get it into the same I want to get it into the same shape as these remaining terms. Where I had this none, uh, in all of these broadcasted expressions, that dimension would have gotten multiplied by n bands. So I'm going to tile this array um, by n bands in that direction. There are a few different ways you could do this, but I'll just do it in this way. And then I'll flatten that. So that corresponds to the whole energy for each term present above. I can similarly compute the electron energy, which is the final state energy for each of them. And that corresponds to this one, which I will repeat that way and flatten that. And if I wanted to keep, I'll keep the whole energies negative. All right. So now I will do another histogram in order to capture these contributions. And I will collect the first. So I'll do a histogram 2D where I collect by the frequency as the first axis and the energy of the electron as the second axis. And I'll have omega bins, and I'll use the same omega bins for the other one as well. So accordingly, I should actually make the whole energies positive. So I'll do this as mu minus that. So it's the energy below the Fermi level is how I'm defining it for the whole. Right? And likewise, I'll collect the whole energies. Right? So the weights remain the same, and I just have those extra factors. And then I should do the same normalization as I had before. Right? And then I should be able to plot that. The one thing I'm going to do here is for the amount of data that we can collect, we are going to get very grainy results. So just to make the results understandable, and our bins are very fine. So I'm going to apply a Gaussian filter to smooth the results a little bit, which also you can see is quite easy, just to the carrier distributions. And that corresponds to a range of the filter that goes over 5 grid points. So about 0.05 EV. Let's prototype this with fewer K first, see what it looks like, and then increase the resolution. Right. I'm just going to look at the histogram 2D. Oh, I see. The bins are collected together into a single argument. All right. Something's not quite right. So this part of the plot is correct. So we have, so this is basically a projection of the plot I had shown to you in the slides. We are going to have the carrier distribution on this axis and the um, photon frequency on that axis. Let me quickly check. Omega and then the energies. Oh, I see, I see. Take this over. There was an additional normalization that I had done here. So in order to plot the carrier distributions, so what I had plotted right now is just the probability density that given a particular carrier and a particular photon frequency, what is the probability? Now that plot turns out to be quite difficult to determine. It's difficult to visualize. It's much easier to ask, if I had a photon of a particular frequency, what is the probability distribution of carrier energies for that frequency such that it integrates to 1? The distribution we currently had integrated to IMEPS instead, which made it really hard to read. So what this part is doing is it integrates each um, it integrates each slice of the carrier distribution. Actually, we don't need this. It integrates each slice of the carrier distribution and then applies that to the corresponding carrier distribution. So it's essentially normalizing each row of that two-dimensional matrix. So let's look at that once again, right? Which will give you something like this. So that essentially evens it out so that we end up with, because if you remember, if you look at the IMEPS, it varies by orders of magnitude from one photon frequency to the other, which would make it really hard to all represent in one kind of color mapped plot. But by normalizing the carrier distributions this way, we can get it all to the same scale here. While we are looking at this, let's run this with uh, the original number of K points. Oh, it wipes that out. Right? So this part hopefully is all clear. We took the same terms, but we histogrammed them additionally by the initial and final state energies that were involved in each transition, right? This part of the normalization was the same as for the imaginary part of epsilon, but we have an additional normalization that we're doing here to define this IMEPS E and IMEPS H to be the probability distribution given that a photon at a particular omega has been absorbed. What is the energy distribution, the normalized energy distribution of electrons and holes that you would get, right? And you end up with something like this. So this is essentially telling you, because you have a you have some structure here, but you have quite a uniform color across, which means that you have an almost even distribution of electrons and holes across the entire energy range. So if I had a photon of energy 2 eV absorbed, I have an almost even probability of producing a hole from energy 0 to 2 eV and a corresponding energy of electron 0 to 2 eV. Of course, each one would conserve energy. But notice some interesting things that happen. Okay, first of all, think about these missing triangles, right? That missing triangle over there is just energy conservation. When I have a photon of a particular energy, my maximum electron and hole energy can only be equal to the photon energy, right? So my limiting cases are I absorb an electron, I excite an electron that's just below the Fermi level, giving me a hole of 0 energy and an electron of 2 eV, or the other way around. But what's happening over here? So there's a missing triangle there and there. Any thoughts? Let me show you. So when I have a photon of energy 4 to 5 eV or 4 to 6 eV, something changes again. But oh, that's a good point, Adam, that the Vanier functions aren't that good above 5 eV. Sure. Um, you're right about that. Actually, I think the energy range was a little bit larger than that. So for the 6 eV was actually the window. So over the range plotted here, that's why I had set it to limited it to 6 eV. 6 eV was actually the energy range till which the Vanier functions are valid. Photons are above the work function. I don't recall what the work function for aluminum is, but the current material that we are dealing with has an infinite work function for the simple reason that we are not describing the surface. Right? The work function requires that there is an outside to the material. Currently, we are describing an infinite three-dimensional material. So the electronic states that we have here, there is no outside the metal. So that's why the absolute energy scale also doesn't make sense here. So remember that everything that is all features that are present in that plot should ultimately be connected to something on this band structure. Yeah. So let's think about where this interband transition giving you the even probability is coming from. It's coming from this band crossing near the Fermi level. So as I expand an arrow that starts below and above the Fermi level, I can find various combinations such that I can have an electron starting here and a hole going up and all that, all the way up to an electron starting below and ending up here. So as long as I'm in this pattern where I have this X and this outer thing, as long as I'm following that, I can achieve any transition such that my electron and hole probabilities are equal, right? But when I end up at about 4 eV, that suddenly changes because I have this band abruptly change direction here. So when I'm at 4 eV, I'm no longer able to do those transitions. In particular, if you look at what's missing here, I can no longer form those high energy holes, which is essentially coming from this band flattening off. So at this point, after I cross this point, I can no longer start transitioning here. That requires a much higher energy. So I'm not, by direct transitions, I'm not able to form holes of energy greater than 4 eV right now, right? Because in order to form a hole of energy 4 eV, I don't just need 4 eV. I will actually need something like 8 electron volts to get up there. So those electronic structure features eventually show up here. So the fact that the direct transitions in aluminum are so flat is actually an exception. Typically, this plot that you have here should be significantly more structured when you're looking at direct transitions. So as an exercise, if you're interested in this, you can look at the tutorials on the website. You can do this for another metal and look at how the carrier distribution looks. It's going to be substantially different from this. Any questions about that code or discussion? Okay, so we're about halfway through this. So let's continue on with phonons. And we'll go through this part a little bit quickly because it's essentially the same strategy as the electron. So we'll be able to do this quickly. So the phonons are described in a very similar way. Instead of Vanier functions this time, the phonons have a very intuitively meaningful localized representation, which is just the displacement of atoms. So analogous to the Vanier basis, the phonon band structure, the analogous quantity is just the force matrix, which tells you when I displace an atom in one unit cell, what forces are applied on all the other on atoms in adjacent cells. So we'll have a cell map exactly like before, right? So I'm not going to repeat that exercise here. We can read that. We can read in the phonon cell map in exactly the same way. We are going to read in the phonon frequencies in exactly the same way. Just to recap this, so this is the real space omega squared matrix. The only difference here is that instead of a force matrix, we are reading a force matrix that is already pre-scaled by the masses. So it's actually a frequency squared matrix, which is why I'm calling it omega squared. So if I diagonalize it, I'm essentially going to get the square of the phonon frequency. It's the harmonic oscillator frequency squared. So omega squared will be, I will read it in from totally dot phonon omega squared as indicated in the comment above, which is just a flat file. I will determine the size, the number of phonon modes analogous to the number of electronic bands just by looking at the length of what I read in uh, divided by the number of phonon cells, right? And once I have that, I can reshape I can reshape this to uh, and then do the swap axis 1 2 as I'd done before, right? So I'll end up reading, so there are, this is just each unit cell has only one atom, so I have a 3 by 3 matrix at each of the cells, and the number of cells here are significantly smaller because the range of the force matrix is a lot smaller than the electronic Hamiltonian in the Vanier basis. All right, so I'm going to copy over the electronic band structure code from here, and we can convert that to a phonon band structure with almost no I went way forward. So we'll once again have a phase. We are going to work with the same k-point path, just with the phonon cell map instead, right? My omega squared in k space will be the same thing. Let's call it that for convenience, right? So that's my Fourier transform portion of it, and then I will get omega squared by diagonalizing this. I can do that but I want the phonon frequency, so I have an additional square root, right? And to plot that, that's just oh, it's already there. Right? So what we have now is the phonon band structure read in from that force matrix file. Right? So exactly the same operations, Fourier transform, diagonalize, that gives us the phonon frequencies, and we have the band structure that way. I'm just going to do a it exactly at 0, it can go slightly negative and so on. So I'm going to add a regularization here, which keeps it above 0. So it removes that warning and doesn't, at the gamma point where the phonon frequencies are 0, it doesn't create that issue. Right? Now, of course, the important difference is here, because we're taking the square root, instead of parabolically going to the bottom at the gamma point, you end up with these linear dispersion relations, the slopes of which are the sound velocities. right? So it's the acoustic phonon modes. Um, and note the overall energy scale. This is significantly smaller. It's on the it's in the sub millihartree scale. We conventionally plot this in milli EV units. So I'm just going to replot that um, in milli EV. Okay. So for aluminum, the maximum phonon frequency is around 40 milli EV compared to room temperature KBT, which is about 26 milli EV. So essentially, most of these phonon modes will have a significant occupation and contribute to all the processes that we are considering. Right? In exactly the same way as we did for the electrons, we can also compute the phonon density of states. So I'm going to copy over the the electronic density of states code once again. Right? So we just have a different, we have a phonon frequency grid, which has to be significantly smaller. So 40 milli EV is where we stopped that because of what we saw in the density of states. Otherwise, the logic is exactly as before, right? We just need the phonon cell map instead. Um, omega squared R. Let's copy this line over. Right, so that's the phonon frequencies now, but the only difference now is it's computed for the Monte Carlo K points, and I'll accumulate that over that. Right? And that gives us our phonon density of states. Once again, notice the different features. You had a parabola that looked this way for the electronic density of states. Because of the linear dispersion relationship, you have G omega going proportional to omega squared at low frequencies. And then, so that would be what you have in the Debye model, for example. And then as you go to higher frequencies, you the crystal structure does matter because it gives you phonon bands that look, that depend on that crystal symmetry. Right? So that linear acoustic part gives you this quadratic behavior here, and then the rest depends on the depends in a more complicated manner on the phonon band structure. All right, so that is the end of the phonon part, which mimics the electrons quite closely. Let me know if you have any questions. Then in the last 20 minutes that we have here, or sorry, last half an hour that we have here, we'll talk about electron phonon matrix elements. We'll pause for a minute or so here if you have any questions about anything up to this point. Okay, let's slowly get to the last part. In this last part, I'm going to cheat a little bit. I'm not going to write the key code from scratch because it would probably take a very long time. So most of the complex part of the code here is already written. So I'm just going to go through it slowly and let me know if you have any questions. We are first going to read in the electron phonon matrix elements, which now have a significantly larger dimension, because what the electron phonon matrix elements are, these are essentially representing a vertex that contain one phonon mode and two electronic modes, right? So everything that we had so far depended on r minus r prime, after using translational invariance. But for the electron phonon matrix elements, it's actually going to depend on R and R prime separately. So the easiest way to think about this is what the electron phonon matrix elements are storing is I perturb an atom in a particular direction in the unit cell centered on the origin without loss of generality. That's where I've used my overall translation invariance of the crystal in picking that unit cell, right? And then I'm asking what is the overlap of this atom perturbation on a Vanier function centered at the cell at R and another Vanier function centered at the cell at R prime. So that's why I have independent dependence on R and R prime. Okay. So if I look at the cell map corresponding to this, first I will just have I have a cell map very similar to the phonon cell map, but it's slightly different because there might be some additional cells used for symmetrizing the electron phonon matrix elements, where I have to account for the positions of the atoms as well as the Vanier centers, right? So that's nothing new. But then ultimately, when I'm reading in the electron phonon matrix elements, the dimensions of that object are shown here. So I have R and R prime going over this n cells EPH, which is what I got here. So 95 in this case. So I'm picking a cell for the first electronic state that I'm considering, picking a cell for the second electronic state. The number of modes in this case 3 correspond to which direction I'm moving the atom in. If I had multiple atoms in the unit cell, it will be number of atoms times 3 in this location, right? And then for each of those cells and modes combination, I can have as many Vanier bands or Vanier centers in each cell as possible, right? So effectively, I have this 5-dimensional object I'm now reading in compared to a maximum of 3 or 4 that we had done so far. Unfortunately, it doesn't stop there. The one additional complexity is that this data is not really stored on n cells EPH. It is stored on the contracted version of this because all cells in this are not unique, exactly as we had done for the electronic Hamiltonian. This is important once again, and it is done for efficiency by the DFT code, because otherwise you'll be storing the same matrix elements several times and it will make these files much larger than they need to be. All right. So in this case, the number of n cells EPH does not correspond to the k-point grid, but rather the phonon supercell size. So it's the mesh corresponding to the phonons, which typically is a lot smaller. For the calculation we are reading in here, it corresponds to a 4 by 4 by 4 phonon mesh. Or maybe it's an even smaller one. I forget what we had read in here. So let's go through this code here. So exactly as we had done before, we had initially obtained the k-point folding from the DFT calculation. This time we are getting the phonon supercell from the phonon calculation, right? Then we are reading in the electron phonon cell weights, which is similar to what we had before, right? But this time it couples a specific set of bands corresponding to the electronic state with a specific set of atoms corresponding to the phonon state. So each of those has a particular weight for the symmetrization. And because it's specified by atoms, the next 2 lines of code repeated to become by mode. Because for each atom, I can perturb it in 3 directions, and the weights are the same for each of those directions of perturbation. All right. And then the last bit of code is similar to what we had for the electronic Hamiltonian. We have to determine this index, which tells you the mapping between the unique cells and all the cells. I read in the reduced matrix elements, which is on the number of unique cells, modes, bands, 5 dimensions, right? And then when I look at the expansion of this, I have 2 places where I need to expand because there are 2 electronic indices now. So I expand along the first index and I expand along the second index. And I multiply by the weights along the first index and the weights along the second index. Now, as you said, you can see why I didn't volunteer to write all of this code again without having to do this iteratively. If we just run this, the phonon supercell dimensions are 4 by 4 by 4, right? I read in from the file something that had, so 4 cubed is 64. So that's what I've read in here. But that needs to then be expanded to this full cell so that I can do interpolation, which is what is in the outer one here. So any questions about that? It's approximately the same operations that we had done for the electronic state, but just a little bit more complicated because we have to do this on 2 electronic indices instead of 1, because the electron phonon matrix elements are coupling 2 electronic states. Yes, so the HEPH Vanier contains the electron phonon matrix elements in the Vanier basis for the electronic states and the atom displacement basis for the phonons. Right, so it's telling you when I displace a particular atom in a particular cell, what is its impact, what is its overlap between two specific Vanier functions at two different cells. So the 5 indices correspond to how I'm displacing the atom. So that's the mode index, and the cells corresponding to the 2 Vanier functions and the indices corresponding to the 2 Vanier functions. Yes. The idea with all of these is that the range of these should be relatively limited, and as I increase the phonon supercell size or the electronic k-point folding, everything should decay exponentially with the number of cells in the cell map. So Ari is asking, how do we get to this notebook again? I crossed out of it by accident. So you should so you downloaded the folder from Dropbox, right? So um, you should have the notebook locally where you've opened it. So do you saying like you closed it and you don't have it saved? If that's the case, then you might want to work with the completed notebook and you do a run all cells so that you get the previous cells executed. Does that make sense? Oh, send the Dropbox link again. Can somebody do that? Can somebody send the Dropbox link? I don't have it. I've closed that tab as well. So this would be on the same Dropbox. Yeah. Okay. Thank you. All right. So going forward, we will need to do processing that couples electrons at 1k and electrons at another k with phonons at a q that couples k1 and k2. Now things will get messy very quickly. So let's first package everything we've done so far into convenience functions. So all this electronic transformation, uh, getting the electronic energies, eigenvectors, velocities, all that code, we can couple that into this function. Um, Instead of the full momentum matrix elements, we are going to focus on the velocity matrix elements alone. So the velocity matrix elements are the diagonal parts of that. So we can just adapt the einsum to do that very quickly. So this calc E function basically just packages everything we've done so far for the electrons. Likewise for the phonons. So you get the energies, the unitary rotations and velocities for the electrons, and the phonon frequencies and the unitary rotations for the phonons. Right? And we can test out these functions by quickly running the electronic and phonon band structure once again, right? Just to demonstrate what these functions are doing. Now, the reason we are doing that is we need an analogous function now to compute the electron phonon matrix elements, right? And that requires this unitary rotation. So we have an electron phonon matrix element in the inner one here. Beta corresponds to the atom perturbation mode, right? And we have its coupling to Vanier function A at cell R Vanier function A prime at cell R prime. You do these unitary transformations which take you to block bands. Then you do this Fourier transform. Now this is a proper double Fourier transform that you have a K prime dot R prime and K dot R, which takes you to a pair of K points. And then you have also a unitary rotation for the phonons, which takes you from the atom displacement to the eigenmode of the phonon, and an overall normalization factor for the amplitude of the phonon displacement, which gives you the ultimate electron phonon matrix element. Sorry, that should be alpha here. I noticed a typo here, so I can just quickly correct that. Right. So you contract alpha beta, and here you have you're summing over beta, and you end up with something that has alpha. So actually, maybe it was correct. Okay. Anyway, uh, yeah, it might have been correct the first time. There might just have been a convention about U and U transpose. Anyway, so you have unitary transformations for the electronic states, unitary transformation for the phonon state, and the double Fourier transform over the two sets of cells that are present in this case. Right now, once again, this expression, the last one, I'm just going to have the code already, and we're just going to talk about it briefly. So I'm going to define a function calc EPH which encapsulates the computation of this electron phonon matrix element. It first computes the electronic state for K1 and K2 separately, right? And then for every, so now these are all vectorized. So K1 can be a list of K points, K2 can be a list of K points. All right. So then for every pair of states connecting K1 and K2, I want to have the phonon properties because that's momentum conservation. The momentum of the phonon has to be K1 minus K2. So I'm running calc pH on this vectorized thing of K1, all pairs of K1 minus K2. All right. Then for computing the electron phonon matrix elements, I have the phases for the two Fourier transforms, one with respect to K1 and one with respect to K2. This is the amplitude normalization function. And then this horrendous list of einsums is basically all the pieces of the unitary rotations and the three unitary rotations and the two Fourier transforms. All right. We could have written all of this as one gigantic einsum involving everything, but that actually turns out to be significantly slower because when you do the index contraction sequentially, you are avoiding some repeated calculations that end up happening if you do an einsum with everything. So this is something to pay attention to when you're using einsum. Right? So each einsum here is only doing one index contraction at a time. Right? And so effectively what this does is if I can test this with a list K1 which has 10 random K points, K2 which has 15 random K points so that I can see the dimensions. When I run this, effectively what it returns are momentum matrix elements for each of the 10 K points against each of the 15 K points for 3 phonon modes, 5 Vanier functions in each. I have the corresponding phonon frequencies coupling this 10 by 15 K points for 3 phonon modes. And then the corresponding electron energies and the electron velocities, which have this extra dimension of 3 for the direction of the velocity. All right. So after this, we will get back to writing the code here. Any questions about this? So once again, should be very similar to the momentum matrix element code that we did before, just several more unitary rotations and 2 Fourier transforms. All right. So in the last bit here, what we are going to do is we are going to compute the resistivity of aluminum due to electron phonon scattering. So there you can do this in a few different ways. One way would be to compute the scattering time due to electron phonon scattering for each electronic state. That would involve evaluate an expression like this. It looks a little complicated, but still fairly straightforward to understand. It's just a Fermi's golden rule again with this matrix element square. This is the electron phonon matrix element, and energy conservation between the initial final electron states and the phonon frequency. The sum over plus minus corresponds to phonon absorption and emission. And then you have these occupation factors that combine Bose factors for the phonons and Fermi factors for the electrons. But when we are doing a transport probability, we have this additional angle factor that tells you each scattering event, how much does it relax the momentum? Because in resistivity, what matters is not just that a scattering has occurred, but by to what extent each scattering event is changing the direction of the velocity or momentum of the particle, right? So we have this velocity factor over here. So it's just 1 minus cos theta between the two velocities. And once you have the lifetimes, if you do a linearized Boltzmann equation, you can show that the overall conductivity is going to be proportional to the velocity squared and this relaxation time with this Fermi function derivative upfront. Now, doing something like this in this Python code is going to be quite challenging because it involves a lot of bookkeeping, because I need to calculate the individual relaxation time for each electronic state and then put all that together. There's an alternate, slightly approximate formulation that we'll work with instead, which goes via the Eliashberg spectral function, and specifically the Eliashberg spectral function for transport. So it's a transport weighted version. So what this does instead is it collects the electron phonon coupling for all electronic states near the Fermi level as a function of phonon frequency. So that's this quantity shown here. So I'm looking at the electron phonon matrix element, and I'm going to look at the electron phonon matrix elements for all electronic states, pairs of electronic states that are near the Fermi level. So I have these delta functions epsilon minus mu that are selecting states at the Fermi level. Each phonon mode has a particular frequency, so I'm histogramming by that phonon frequency. If I had just stopped it there, that would have been the Eliashberg spectral function. I throw in this additional velocity scattering factor over here, and that makes it the transport weighted Eliashberg spectral function. And you can show that once you have the spectral function, you can compute the conductivity as a function of temperature by integrating the spectral function over the frequency with a particular moment of the Bose factor, which is what is present here. It's like a Bose prime with some extra factors. Right? So this is the approach we are going to take because it looks more like what we've done before. We will collect the spectral function as a function of phonon frequency and then compute these integrals to get the resistivity. And we will do that in the next 15 minutes. All right. All right. So what we are going to do is we are first going to take the DOS code and we're going to modify it to collect the relevant K. Because what's going to happen is there's a lot of K points. Most of them will not have any states near the Fermi level. And we don't want to waste our time computing electron phonon matrix elements for those states. So we are first going to do a pass through the K points and pick out relevant K points. So let's look at whether there's any state that's near the Fermi level. So what we are basically calculating is whether E minus mu is close to 0. And we'll use a Gaussian to calculate that. So I'll do exponential E minus mu by E sigma. That's the Gaussian broadening. Right? And I have a normalization factor, which is square root 2 pi multiplied by the sigma. So this is going to be my weight for each electronic state, whether it is close to the Fermi level. And then I can find, and this is just per electronic state, and now I can find which states actually contribute. Right? So what I'll do here is I look at the maximum weight I look at the maximum weight along the axis, along the last axis. So I'm computing the maximum weight across all bands for a given k point. And my selection is going to be where this is greater than some cutoff. Let me just see what cutoff I had used here. Right. So 10 to the negative 3 over E sigma. All right. Right. So this is my selection. And then I can append to the list all k points which I've selected. I'm also collecting the Fermi velocity and the total DOS here, right? I'm just going to copy that code here in the interest of time. Right? So I'm computing the density of states at the Fermi level because this corresponds to the weight that a particular state is at the Fermi level. When I add it up, that just adds up to the density of states at the Fermi level with a Gaussian broadening. And if I weight that with the velocity squared, then I'm going to get the Fermi velocity squared. This should be max, not maximum. Right. So once I get that, by taking this sum divided by that, I can compute the average Fermi velocity squared and Fermi velocity at the Fermi level, and I'll have the density of states at the Fermi level. And this is then reporting how many k points I've selected that are near the Fermi level. Once again, let me prototype this with a smaller number of k points, make sure it works, and then go to the larger number. All right, that appears to be correct. All right, so this is the first pass that is selecting the relevant k points. And then we will work on all pairs of k points drawn from this set to compute the electron phonon matrix elements for the Eliashberg spectral function. So the logic of that code is we go over several blocks of a certain number of k points. Again, all of this is partly driven by how vectorizing in Python will work well, right? So we take 32 k points at a time so that we don't waste our loop time. And we'll select 32 random k points out of the list that we've generated, which has 3,900 k points that contribute near the Fermi level. For all pairs of those 32 k points, we will compute the electron phonon matrix elements and do the contributions to that. We could have also just gone over all k points here. That would have been a significantly more expensive thing. So for a quick demonstration here, we are doing this additional Monte Carlo subsampling to get a quick result. Right. So now we have the electron phonon properties, right? So we've just called the calc EPH to get that. Now we need to do the various terms that give us the Eliashberg spectral function. So first we need to do the velocity direction factor. So we'll compute the unit vectors along V1 and V2. So remember that the shape for each of them is number of k points by number of bands by the direction in the last one. So this would just be V1 multiplied by, I can do the norm of V1 along the last axis, but I have to add that axis back to broadcast. Right, so this is basically just normalizing each vector. Similarly for V2. And now I want to compute, so each of this is n by n bands by 3. Now I want to compute the direction between the two things. So my V factor the v1 dot v2. Let me do it with INSUM just to keep it easy to read. So I have a k point index, then a band index and a Cartesian direction index. For the second one, I have a different k point index. Let me call it L, a band index and the Cartesian index. I'm going to contract the Cartesian index and I'm going to keep the remaining indices. Right? And the factor also has a 1 minus, because it's so that will basically give me the cos theta for all of those pairs, and this gives me the 1 minus cos theta. Because we are short of time, let me verify that. KK, okay, AB. So I want the ordering that way. Oh, I like that notation better. I'll use a capital K for the other K point, and I want to order them that way. The two K points together, and then the two band indices together. Right? Now I need the contribution that has the matrix elements and the velocity factors, and we're going to sum it up over bands. So coming back to the spectral function up here, right? So what I've computed so far is this. I have the matrix element squared, which I can readily get, and I'm going to sum that up with the delta functions over all the bands so that I have something that just is a function of the phonon frequency. Right? In order to do that, I need the weights again for the two states, which is exactly what we had here. Right? So these are the delta function weights. All right. So I have the weights of the two electronic states. I have this velocity factor. I have the matrix element squared, which is just going to be the absolute value of that squared. So the overall term that I will have combining all of this, once again, doing this using INSUM. So I'll have absolute value G squared, W1, W2, and V factor. So I have four things that are multiplied together. The V factor has indices KKAB, as we had before. This would be much more, I mean, this can be done without INSUM, but it's just much more convenient to write it with that. The first electronic state weight is essentially K and A. The second electronic state weight is K and B. And the electron phonon matrix elements have K, K, phonon mode AB, right? And I'm contracting all of that to get something that goes by the two Ks and just the phonon mode. So this is basically a list of all the phonon modes. So this will have the same dimension as omega pH. And once I have that, I can readily histogram this by phonon frequency. So term is what I'm omega pH is what I'm histogramming because it's a spectral function. The weights is term. I should flatten both of these. And the bins that I'm going to use are the same as I had before. All right. So when I do all of that, oh, that actually ran. I'm surprised. So I collect the spectral function. The overall factors from the expression, from the analytical expression we had is present here. So you have that d omega and the overall value here. In addition to that, we need to account for the fact that we have subsampled, right? Because we have not gone over all pairs of K points. So this is accounting for how many K points there were overall and what fraction of them we actually sampled, so that we are representing the overall expression, which ends up with this spectral function that looks something like this. And let me just make sure, yeah, that looks about correct. It's about right. All right. So that gives us the spectral function. again as a function of phonon frequency. So it looks somewhat similar to the density of states, but this now includes the electron phonon coupling in there. And in the last step, we can integrate over the Eliashberg spectral function to compute the final resistivity. So we first want h bar omega over kBt for all contributions. So this is going to be omega mid by t. But we are doing this for several temperatures all at once. F and both terms. So the omega axis should be first. Yeah. Right. So I vectorize it that way so that I go over all pairs of omega and t. My Bose term is going to have a bunch of exponential beta omega divided by if I'm not mistaken, this is what I need to calculate. Right? So beta omega e to the beta omega divided by e to the beta omega minus 1 squared, which I think I got correct. Yeah. And then you just integrate over that with this dot product, which will give you the result for all times together. And then to compute the resistivity, I just have a prefactor Bose term. Oh, thank you. Yeah, thanks. And then to compute the resistivity, my overall expression. So that's this integral, right? And then I will be dividing the. So then I have this overall prefactor in addition. I have the VF squared computed already, right? So that's going to give me the conductivity. So I want resistivity, which is 1 over sigma. So I'll have 3 divided by VF squared, and then this integral. So 3 times 2 pi. So 6 pi divided by VF squared times the integral. Right, I clearly did something incorrect. Oh, this should have been omega pH mid. I had the wrong frequency there. Something is not right. Oh, I forgot the unit cell volume. That was the other piece there. Right? So that's our predicted resistivity as a function of temperature. We actually get a pretty decent agreement for this approximate treatment to about 10 to 20%. We can do significantly better if we go with the full technique where we account for each individual band velocity. The Eliashberg spectral function version does make an approximation analogous to the relaxation time approximation, where it says that all the electronic states at the Fermi surface relax with the same time scale. So that introduces some errors there. So I ran out of time there, but hopefully you got a flavor for how far you can go with some relatively simple Python code once you've read in these ab initio matrix elements. And I'm around for questions. And you can do a lot more with these spectral functions. If you compute the Eliashberg spectral function